Okay. And if you try to apply, if you again see from the x-axis point of view, so actually these two are not same. If you take a mirror image, do they look same? So this kind of structures are called not centrosymmetric along the x. If I take the axis as x, it is not symmetric along the axis x. And even if I take the axis y also, this is not symmetric, because this is not the mirror image of the other. So this kind of materials, if you apply some force on them, what happens? In the atoms, in the atoms there are electrons. You know that, right? So there is some displacement of the electrons. In normal case, when there is no force, all the charges are balanced. But if there is a force, and if it is a non-centrosymmetric structure, of course the electronic displacement is going to happen. And as it is non-centrosymmetric, as it is not a mirror image, so you will not have the charge balance. So there will be some extra charge. Am I understandable? Okay. So that kind of material gives piezoelectricity. So it's not all the materials give certain kind of materials.
So whenever there is an asymmetry,
yes,
it will
they
give.
Yes, they will give. And maybe if somebody can. Yeah. So here also it is just a schematic saying what is piezoelectricity. So this kind of material, non-centrosymmetric material, when you apply force on them, they have some charge displacement, electronic charge displacement, and they are giving electric field because of the charge displacement. It's not getting zero or neutral. And the same material, also the other thing happens, which is called converse piezoelectric effect. Like if you apply electric field, there will be deformation in the material. So this property actually you can use for actuating application. Like I was giving the example of pressing a buzzer. Or pressing a door switch, electronic door switch. When you press it, it senses the pressure and it generates some kind of electrical or electric field. So that will be sensed. So that is the direct piezoelectric effect happening. And suppose the buzzer, when the power is off, so there is certain program written that it monitors the power level, and when the power is below that, so it applies certain kind of electric signal across the material, and it deforms and it generates the sound. Okay?
How that converse piezoelectric effect happens? Like, in that case, if you have a force that charge is not symmetric, so the extra charge and that current will come. And like in this converse piezoelectric effect, if you apply electric field, how?
So when you are applying electric field, in atoms what are there? Electrons are there, right? So electrons are getting affected by electric field. So when you apply electric field, there is also electronic displacement.
Then in non-centrosymmetric case also there will be electronic displacement, right?
But there is a charge balance, because how much it is displaced there, that much is displaced here also, bottom also. So actually it adjusts both the things. But in non-symmetric cases it doesn't happen.
So material will reshape in such a way that it should balance. It will get balanced.
Yeah, in normal material, like if you take a normal material, or if I take a centrosymmetric material, if I apply electric field, there the disbalance will happen. But because of the centrosymmetry, it will adjust itself. So you will not see any extra effect. But it is happening, but it's making it zero, plus minus. But in case of non-centrosymmetric material, this will not happen. This plus and minus is not getting cancelled. The amount of plus charge generated and the amount of minus charge generated, that is not getting cancelled. So you will have some extra charge in the material. So that will give you piezoelectricity. Is it clear? So as I was telling, that the piezoelectricity is measured by piezoelectric constant, and the piezoelectric constant here it is I have mentioned it by D, and you see there are some numbers there, 3, 3, 3, 1, 1, 5. What are these things? Yeah, y-axis.
Applying current.
Can you be a bit louder?
You're applying a current in that direction.
And what happens if I do not apply in that direction? mean, is it really important to, to have these terms?
Yes. Yeah.
Why?
You have to see the balancing of the electron, right?
Mhm.
You have to see how it is behaving in which axis when you apply electric field.
Yeah, so when I say centrosymmetric, I'm saying it with respect to some axis. Probably the material is centrosymmetric about x-axis, probably it is not in y-axis or z-axis. So that is very important, that in which direction you are applying. So for that, is it 3, 3, 3, 1, 1, 5, these are coming.
So A33 means it is not centrosymmetric with respect to the z-axis.
Yes, suppose if you take z as 3, x, y, 1, and if you take z as 3, so if you apply, you can see here also. If you apply force in this direction, you will have the electric field also in this direction, because it is not balanced in this direction. And there are certain materials that they will have only one probably, which we can measure. It's not that always that all the directions they have very high value, measurable value. So that kind of thing happens. And there are also 1, 5. So 1, 5, what is that? Suppose that you have some kind of rotational deformation. Then also it can give you with electric field. So that kind of things are denoted by this 1, 5 or that. Then you can see that I have made some circular pattern on the axis. So these are denoting that. And so this piezoelectric constant, so it should, if we try to find out that how express them in terms of an equation. So like deformation, I talked about deformation, I talked about strain, I talked about stress, I talked about electric field, and I talked about electronic displacement also in the material. So we need to find out how these terms are related. Then actually we can have some measurable piezoelectric constant. We can measure piezoelectric constant through the equation. So these are the two equations. So here you see this D is that D, and E is electric field, and T is strain, S is stress, and D is electric displacement. And there are two other terms also. This is small s and this is epsilon. So this is also very important, that this is called the material dependent property, this epsilon. So it varies depending on material. And it is also called relative permittivity or dielectric constant for some materials. And this S, this represents compliance, which is actually inverse of stiffness. So how stiff a material is, that is also very important, because then only, when you are applying pressure, if some material is not that stiff, it will have more strength, and if some material is very stiff, you cannot deform it much. So this gives that information. So we have a, understanding how we can relate them. So whenever you suppose you are also working, it's not needed that every time you mug up an equation, you know that what are the parameters which are affecting the work. So try to understand that how it's increasing, decreasing, and maybe things can be complicated also if you take more parameters, but the general equations are formed that way. And so enough of piezoelectricity. Now I'll talk about nanomaterials. What are nanomaterials? Anybody? Chinman, you are working, right? On nanomaterials. What are nanomaterials?
This has the length 10 power minus 9.
Okay, which Sukanya, did you understand what did he tell?
He said that the materials which has the length 10 to the power 9 nanometer.
10 to the 9, no, 10 to the minus 9.
Minus 9.
Yeah, what does it mean? Minus 9 meter, yes. What does it mean?
It's too small.
It's
How small?
It's like if you have a material then and you are looking at if any of its dimensions are of the range in like 10 raised to minus 9 nanometers, then that particular material, we are visualizing it in that particular range. So we can identify them as nanomaterials.
So he told one thing, that very small. How small? Can you see them? in your bare eyes?
No.
No. Okay. So what is a nanomaterial? It's good for my next slide. So generally whatever we see, whatever we know, all the objects, we put them in a length scale. And like you can see here, there are different things like universe. So it's nearly 10 power 30 meter in range, and then you see a galaxy, and then distance between sun and earth, and then here comes, I think, Mount Everest. So what is the height of Mount Everest? In which range?
Kilometer.
So you can see that 10 power 0 meter, that's 1 meter, and from there. So, and there is an ant also. So generally the size of ant is like few centimeters. So few centimeters. And then there is a hair, single hair strand. There around the range of micrometer. Micrometer is 10 power minus 6 meter. So which one is more, 10 power minus 6 meter or 10 power minus 9 meter?
10 to the power minus 6.
It's more, right? So that means it's almost 10,000 times smaller than a meter, right?
What is the question?
A hair, it's almost 10,000 times smaller than a meter, right?
Make it
10 to the power minus 6, 100, 10 to the power minus 6. So,
It's around 100 micrometer.
make a hair,
Yes.
make a hair, and 1,000 times you make it small.
Yeah, if you make the length small, I mean not lengthwise. if you-
Lengthwise.
Yes. And so it's around 100 micrometer. And now there comes nanomaterial. As Sam was telling that one dimension
did we
of...
answer the question for Sukuna? Sorry.
No, I didn't answer. I told it's micrometer.
Who asked the question?
No one asked.
She was explaining.
No, I was
She was.
So no, actually she told that there were minus 6 micrometer, there were minus 9 micrometer. I was asking her